Welcome back. Today's topic is about Coulomb's law. In the last video lecture, we have discussed about the vector transformation from one coordinate system to other coordinate system, and we have also seen the different terms which we will be using in static electric fields. We have gone through electric fields. We have also seen electric field intensity, and we have also discussed about electric flux and electric flux density, right? So electric field intensity is represented as E, units are volt per meter. Electric flux is represented by psi, units are coulombs. Electric flux density is represented by D, units are coulombs per meter square. And E and D both are vectors and they are related by. This is what we have discussed in the last self-learning topic. Moving ahead, in today's class we will discuss about Coulomb's law, and I hope that by the end of this video lecture you will be able to compute the force of attraction or repulsion between point charges using Coulomb's law. Now, coming to the introduction, the famous scientist and physician Charles Augustin de Coulomb in 1785 proposed this law, which refers to interaction between 2 point charges. So he proposed that if there are 2 charges, Q1 and Q2, there exists a force between these 2 charges, and the force is proportional to the magnitudes of these charges, and it is inversely proportional to the square of the distance between them. And the direction of this particular force is along the line which joins these 2 charges. Either it will be in this way or it will be in this way, but it will be across the line, along the line joining the charges. This is what proposed by Sir Coulomb. Now, putting all these things together, basically what we can write is, see, let us suppose if there is a charge Q1 here and there is a charge Q2, and these are separated by the distance R12, which is the distance between charges 1, 2. Now, the force is along the direction of this particular one, along the line which joins Q1 and Q2. Now, if you carefully see, as mentioned earlier, F is proportional to Q1, Q2 by the distance between these 2 here in this case is R12 square. And I can, instead of proportionality constant, I can use K. So F is equal to K Q1 Q2 by R12 square, and the direction will be along the line of the charges. So it will be, if U is a unit vector along the line of charges, so this is the formula for force which is being exerted by Q1 on Q2. Now let us suppose if I want to determine the force which is exerted by Q2 on Q1, this is F12, F21. So it is Q2 Q1 by R21 square into U21. If you see, both magnitudes are same. This is the magnitude. The magnitudes are same in both the cases. The difference is the direction of the vector. U12 will be in this direction. U21 will be in this direction. So the force exerted by Q1 on Q2 and Q2 on Q1, both will be of equal magnitude but opposite in directions. This is what I have written here. F12 and F21 both are equal magnitude vectors but in opposite direction. Now, let us suppose if I do have a medium, basically, that particular medium basically is given by some measure which we call it as permittivity, relative permittivity. Normally, as we have seen in the last thing, it is 1 minute. we have seen that the force now is proportional to q1 q2 by r square, and there is a unit vector along the direction of these charges, and we have mentioned a constant, right? Equality constant. And this equality constant is given by 1 by 4 pi epsilon naught, where epsilon naught is called as a permittivity of free space with the value of 8.854 into 10 to the power of minus 12. So this 1 by 4 pi value, you know, 3.14, epsilon naught value is this one. So if I do have 1 by 4 pi epsilon naught, 1 by 4 into 3.14 into 8.854 into 10 to the power of minus 12, I can directly write this value as 9 into 10 to the power of 9. This will be helpful for you in calculations fastly. So try to remember this one. Otherwise, you can directly use 1 by 4 pi epsilon naught. And let us suppose if I place this two charges in a medium, then automatically I must write an additional term here. K is equal to 1 by 4 pi epsilon naught epsilon r. This is called as relative permittivity. And it varies from medium to medium. So my final expression is f is equal to 1 by 4 pi epsilon naught epsilon r q1 q2 by r into ur. If I take it from 1 to 2, effect of 1 on 2, then it will be ur1. This is also r1 square. Now if I take it as 2 1, it will be 1 by 4 pi epsilon naught epsilon r q2 q1 into ur2. As already been said, both will be having equal magnitude, and the difference will be only in the direction. So the magnitude is same. This is the magnitude. Okay. So let us suppose when there are multiple charges. We have already seen this one in the last video lecture itself. These forces basically, Coulomb's law basically satisfies superposition theorem. So which means that let us suppose if there are three charges, q1, q2 and q3, and there is a charge q here. Now all of these charges, let us suppose if they are exerting forces on this particular q, the resultant force is nothing but vector sum of all these charges. So superposition theorem is satisfied by Coulomb's law. So that's why I have mentioned here. If there are multiple charges, the resultant force is nothing but vector sum of all these forces. Okay. So that's why I have mentioned here. F1, this is the formula. F2, this is the formula. F3, this is the formula. So the summation of all charges. And one more thing is, the charges basically, they won't be generally of point charges. They will be of different configurations. Most of the times they will be distributed charges. As mentioned earlier, they can be line charges, surface charges and volume charges. Now let's have a quick look about the different types of charges which we have already gone through. Now see here, the charges can be of the form of a line, or they can be just like a surface, or they can be just like distributed over a volume. So if it is spread over a line, it is called as line charge. If it is over a sphere, it can be a surface charge. If it is spread over a volume, it is called as a volume charge. So whenever you are employing this line charge or surface charge or volume charge, normally what happens is they will mention you only a density of the charge over this one, and they will specify the dimensions. So you need to calculate the charge first. So what they will mention, let us suppose if the line is given for you, they will mention that it is having 10 coulombs per meter, and the charge is basically 25 meters of length. So which means that 10 into 25, this is 250 coulombs. Now let us suppose if it is an area, what they will do is nothing but they will mention that it is 10 coulomb per meter square, and the shape is basically a square, and what they will say is nothing but the square is extending from this side of a square is from 0 to 4 meters. So now you are supposed to know what is the area of a square. It is normally s square, and side is already given as 4. So 4 square, it is 16. 16 into 10 is 160. This is in case of a uniform shapes, but most of the times it won't be of uniform shapes. So generally we use differential elements and then we will integrate. So coming to differential elements, how to employ them. For a line charge, if it is in XYZ mode, then it can be in X direction or Y direction or Z direction if it is a Cartesian system. So if it is in X direction, it will be considering it as dx, dy and dz. In case of cylindrical, I'll take it as r phi z. You know that phi doesn't have a dimension like meters. So to make it uniform, I'll take it as r d phi. Whereas in case of spherical, here only this one is of uniform meters type when compared to others. Both of them, they don't have that meters type similarity. So I'll use it as r d theta, and here for phi, I'll go with r sin theta d phi. Okay. Now charge will be computed with this formula. Now this is for surface charge. If it is in the z direction, I will be counting dx and dy. If it is in x direction, dy dz. If it is in y direction, dz dx. Similarly, here in this case, if it is z direction, I will take r dr into r d phi. So like this, this is the surface charge densities. So I am supposed to go with the double integral because it will be having 2 dimensions. So 2 dimensions I am supposed to integrate. In case of volume, I am supposed to go with 3 dimensions. I am supposed to integrate with r, with respect to theta, with respect to phi. The order is your choice basically. Okay. Now let us suppose if most of the times they will give you like this. The charge density lambda is equal to 25 coulombs per meter. And it is a sphere, and it is a sphere of length 5 meters. So what you will be doing? Integral q is equal to integral lambda dot dl. Because it is a sphere, I will be considering it as this one. So what I will write? Lambda, I will consider dr, and r is varying from 0 to 5. Sometimes I will ask to radius varies from 1 to 5 meters. So which means 1 to 5. Now physically speaking, what does radius vary from 1 to 5 meters? Which means that there is a sphere. Okay, there is a sphere. This is the center of the sphere. Now this is up to 1 meter. And this is up to 5 meters, let us suppose. Okay, now this is 1 meter and this is 5 meters. Now what does it mean that the radius of the sphere varies from 1 meter to 5 meter? Which means that the charge is located in this region only. The charge is not located inside this particular region. The charge is located. So now what I am supposed to do? In order to determine the charge, I am supposed to integrate it over lambda. Dr r varies from 1 to 5 dr. Right. So these are the equations which we will be using for determining the charges. So once the charges are determined, then again we will go to computing the forces. So that's it for today. In the next video lecture, we will try to solve a few problems on this one. Thank you.